My name is Collin Christy. I am a graduate student at the University of Arizona working with Kate Alexander, and today I will be talking about the really weird things that Assassin 19BT appears to be doing in the radio. So we've had some really good radio talks so far, so I don't really need to harp this point, but I think we all know by now that TDEs like to do really cool things in the radio, and we don't really understand why that is happening. For a brief refresher of the types of emission mechanisms for the radio, in the radio that we see for TDEs could be something, that was seen early on with something like Swift J1644 plus 57, which I believe is the now front runner for favorite TDE. So if you disagree with that, use your electoral power. There's also been some claims for maybe something that was viewed off axis, a relativistic jet viewed off axis. What was seen early in the field with Assassin 14Li is maybe we are seeing some sort of non-relativistic outflow that could be due to a number of different things that have been discussed so far. Maybe an accretion-driven wind, an unbound debris stream flying out and hitting into the nuclear material surrounding the black hole, or some sort of collisionally induced outflow from the streams intersecting. No detectable emission is also a form of emission, which is interesting because you should expect a lot of messy things are going on. It's not clear why you would not see something in the radio, but we see that a lot of things actually like to do something maybe more weird, as we just saw earlier today. Assassin 15OI was doing, nothing super detectable at these early times, and then you see a flare, and then there's evidence of another flare, and a project actually showed that the second flare was also doing really weird stuff. And Yvette also discussed in her talk that it seems to be extremely common for TDEs to show bizarre late-time radio emission, which is not fully understood. So that brings us to the sort of point of my talk today, is to talk about Assassin 19BT, or 2019 AHK. This TDE got its claim to fame for being the first TDE detected in a test field, which is really cool. Not only was it in a test field, it's in the test continuous viewing zone, which means that you can actually see, well, it's not really, I don't know, if you squint, maybe you can see it. It's between the LMC and the galactic plane. And since it's right there, you can basically see it turn on, which is what was seen by tests in Assassin in 2019. I'm impartial to the Assassin name because for years I used to work for the Assassin collaboration, and every morning before lunch I would have to stare at thousands of these images to look for transients. So a little bit of PTSD there, but still fun. But yeah, I mean, this is a really beautiful light curve. We saw some weird looking optical light curves. This is actually a really nice light curve. And in the discovery paper, Tom Poloin and others looked at the UV and optical properties of Assassin 19BT and found that, it is pretty normal. It showed pretty consistent luminosity, temperature, radii, and spectral evolution as you would expect for other TDEs. And on the other hand, in the X-rays were actually super weak. Had really weak X-ray emission and a very hard spectrum, something that Tom pointed out might be evidence of some sort of jet we might be seeing. So what about the radio? Well, let's see. So we, for this study, looked at nearly 4 years of radio monitoring for this source with ATCA, Meerkat, and ALMA. And right around peak, we also got to DDT observations with Chandra and have nearly 4 years of Swift XRT monitoring of this source. So what did we find? Well, for the first year, we have some radio detections, which is cool. We have an ALMA light curve, which starts detectable and then fades into obscurity. And at early times, we have something that is peaking around 5 gigahertz, which is really cool. And then, months later, we have an SED that is peaking somewhere around 2.1 gigahertz. And the next time we checked on it, surprise, surprise, it got brighter. And it got brighter in all frequencies. And you can also see that the peak emission is now at a higher frequency, which is not something you would expect for a sort of singular outflow model slamming into this ambient material. What this looks like in context of other TDEs is we have, some great candidates for favorite TDEs over here. I gave a couple shout outs to the ones we've seen so far. Assassin 19BT looks like this. The early time looks like something that like Assassin 14LI was doing. And then at late times, it seems to have changed its mind and wants to do something else. We saw a plot like this earlier, I think on Tuesday, of a beautiful sample of X-ray light curves for TDEs. And in the discovery paper, it was mentioned that the X-rays were weak. How weak are they? They're extremely dim. From this paper, it's actually the least X-ray luminous out of all of the optically selected TDEs from the sample. And I don't show all of the Swift upper limits, but this extends basically to 1600 days, and it never rises. So we have a lot of radio data. We can fit some SEDs. So this is also something to note out in sort of in the same way that Assassin 14LI had an archival detection in the radio that was then host subtracted, and all the analysis in the radio was done on the transient component. We also have an example where there was a marginal host detection in the radio that we then subtract. We get some beautiful, seemingly self-absorbed synchrotron spectrum. And we also encounter with our ALMA limit, upper limit, we constrain a cooling break, which means we don't have to make any extra equipartition assumptions. We can constrain this epsilon b parameter, which is the fraction of the total energy that is imparted to the magnetic field. So as was briefly discussed during the last section, we can do this sort of equipartition game to get a good estimate on the minimal energy and the size of the emitting source. And what you need to do this is you need an estimate of the peak frequency and the peak flux, in this case the peak flux being the self-absorption frequency. And you can see that the peak flux just kind of keeps going in a sort of opposite fashion of 18 HYZ. It plateaus where HYZ is going to the moon, which is interesting. And also interestingly, the self-absorption frequency is declining over time, and then seems to be briefly rejuvenated, which isn't really something you would expect for these types of things. So say we take our model of, our first model that we looked at for the emission was, what if this radio emission is due to some sort of spherical blast wave from the accretion process? It's a messy thing, lots of bits thrown out, and it slams into the surrounding material, and that surrounding material then gets accelerated to some power law distribution of energies, and then that is going to emit synchrotron radiation. So what do we find if we model it like this? Well, we find that we get something that is pretty typical for these sorts of things. We have an outflow that is around 5% C. But more notably, what's interesting is that there seems to be two different, radius over time behaviors, which is not something you would expect for a singular blast wave. We also find that the energy increases extremely by almost a factor of over 1,000, but as we heard earlier, that this is not really a robust measurement of the energy, because we always should take this as the minimal energy, but it is interesting because this level of energy increase has not been seen using these same sort of methods. We also find that with the estimate of a radius of the emitting region at a given time, we can speculate what the velocity should be, and we find that the outflow takes on 2 periods of seemingly accelerating velocities, which is not something that has been seen before and is difficult to explain given a single blast wave expanding. We also find that since there was a bump in the self-absorption frequency, that seems to be tied in and causing a implied discontinuity in the radial profiles of the magnetic field strength and the ambient medium density. So some questions about why this is weird. Why are we seeing acceleration? And why does this show some insane 3 order of magnitude increase in the energy when other TDEs studied this exact same way don't show this? Very weird. So as we've also heard earlier today, what if, the X-rays were really dim? So that might mean there are some viewing angle effects going on. So we also looked into the scenario where maybe we are seeing some sort of relativistic jet launched off axis. With this very beautiful picture I love. This is us, and here's a jet. What does this look like if we see this jet from off axis? Well, we see something that expands at super relativistic speeds because we don't see extremely luminous radio emission, like we did see for Swift J1644 and 22 CMC. So for us to not see that, it needs to be extremely beamed away from us, because if it wasn't, then we would see it. So the off-axis jet model in the blue here, this is something that's a little bit off our line of sight, and as you go towards the yellow is the maximally off-axis case at about 90 degrees. You can see for the maximally off-axis case, we get something that is around a gamma of 10. I will show different plots soon. As for the energies, the energies, we modeled them for the case where the opening angle of the jet is truly spreading as 1 over gamma, which is the beaming area. This is the emission that you can see. And in the case where the jet is truly not opening, there is a fixed opening angle, we can add an additional correction factor to the energy for the unseen material that we don't see in the jet. And in both cases, we get something that seems to rise up to somewhere around 10 to the 52 erg, which is consistent with other jetted TDEs. Unlike the non-relativistic case, instead of an accelerating outflow, we see 2 periods of deceleration, which is, you would expect jets to decelerate. They, slam into stuff, and then that slows down the jet. But what is troubling here is that, at early times, you see something that starts at a Lorentz factor of, teens-ish and goes down to a Lorentz factor of a little bit less than 10. And about a year later, you get something that has not decelerated completely, which is not something you would expect, considering that we saw Swift J1644 decelerate to non-relativistic speeds after about 500 days or so. And again, you also get this weird discontinuity in the radial profiles of these, the magnetic field strength and the density. So the big question from this interpretation is, how the heck do you get a jet that exists like this when you should expect it to sort of do what you expect jets to do, which is to decelerate the more material that you sweep up and smack into. We also take a look at the energy and velocity of SAS and 19BT. This is a similar plot that I think Yvette showed on Tuesday. These are all the late time rising weird TDEs, which is really cool. And then there's our leading candidate for coolest TDE, Swift J1644. And if I look at the non-relativistic model here, I get something that wants to be everything. You can see at early times, you get an accelerating outflow with increasing energy, and then at late times, you get still something that is increasing. And again, with this energy increase, I sort of briefly alluded to it. Energy increase has been seen in other TDEs doing this same sort of game, but not 3 orders of magnitude. That is not something you would, at least, I get that it is not a robust measurement of the energy, but it is not clear to me why you are seeing that amount of energy increase when you don't see that, 3 orders of magnitude increase for these other TDEs. Energy increase has been, or energy injection has been implied for other TDEs, such as Swift J1644. You could see it, rises by a factor of about 10 or 20 or so. And some say this might be evidence for some sort of structured jet where the jet's launched with a wider range of gamma factors, or maybe we were viewing the jet from slightly off axis, and as the jet slows down, the beaming area opens up and you're seeing more emission. And here's the off-axis jet solutions for both of the jet geometries. And you can see it's sort of tracing out what Swift is doing, but for much higher Lorentz factors, which is hard to explain. I also show here, it's a bit difficult to see, but in these circles, this is actually 2018 HYZ, using the same prescription that Matsumoto and Purin described for a off-axis jet being, a relativistic jet being viewed off-axis. And you can see at the later epochs, it's actually pretty consistent with what you would expect, or what you get by modeling HYZ the exact same way. But again, it's unclear how do you get a jet to be that relativistic for that long. We can also look at the densities and say, what do the densities look like? For the Newtonian solution, we find at the early times, we are tracing out something that is consistent with a Bondi accretion history. And after the rebrightening, the density profile steepens to something as r to the -2. And in the relativistic case, we have a whole bunch of craziness where you have at early times a super steep density profile as r to the -4, and then something that softens to r to the -2.5 at the later epochs, which is consistent with something like Assassin 14 Li and the early stages of Swift. J1644. I should also note that if you model 2018 HYZ the exact same way, you get something that is consistent with the density profiles at these later times. We also, you might have been thinking, you know, the early time radio emission, the late time radio emission, they look like completely different things. So what if we treat them as completely different things? In the same way that Yvette showed us on Tuesday, if you get a robust measurement of the radius of the emitting region at a given time, you can sort of play a game where if you draw a line backwards, you should expect this outflow to move freely until it sweeps up an equivalent amount of mass in the ejecta. And we can see that just by fitting a line to the data, what launch date does that imply? If we just consider all the data as arising from a single blast wave, we get a launch date that is around peak optical light. I should also mention this is a beautiful assassin light curve, you know? And you can see, one thing that's interesting is that there's a lot of weirdness going on in the radio, but the optical doesn't seem to care, which has sort of been a theme of this week. You have a beautiful t-squared fireball rise, and then this t to the minus 5/3 parallel decay, which again is nothing new. If you trace back this all the data, you get something that is launched around peak optical light. If you take just the early epochs, you get something that is launched about 2 weeks later, which you could say, you know, sure, but this is troubling when our first ALMA detection is around peak light, which means that the outflow that would have been responsible for the radio, if we did see it, we saw it exactly as it happened, which is, you know, a bit of a tooth fairy hunt. I don't think we're that good with our observations. If you fit the later epochs, you get something that is launched about 200 days after the optical rise, and it's actually consistent with our observing gap. So maybe this is the second outflow that we are seeing, and it is just launched 200 days after the optical peak, or after the initial optical rise. So with that, I also wanted to mention that if I do this equipartition game and say maybe the later epochs are just something that it was launched 200 days later, and if I look at the observed peak flux and frequency and find these same physical parameters, the discontinuity is still there, which is not easy to explain. And with that, hopefully I have, you know, made a good case for Assassin 19BT being an interesting TDE. I don't know about best TDE of all time or your favorite TDE of all time, but it is certainly a weird one. A few takeaways are that Assassin 19BT is interesting, but it's uninteresting in the sense that it's joining a large group of TDEs that seem to do really weird radio things at late times. The X-ray emission is extremely faint, which might be a result of these orientation-dependent X-ray reprocessing models. We looked at two different cases for the radio emission, either being arising from a spherical blast wave expanding into the circumnuclear material, or we are looking at an off-axis jet. And we find that neither provides a holistic explanation for the radio emission. And the real takeaway is that a more complex model is needed. As mentioned a couple times this week, to truly test this off-axis jet case, extended radio observations, and especially VLBI, would really lead to a smoking gun case for a delayed off-axis jet. So with that, I can take questions. Thanks.
All right, Paz.
Yeah, thanks. I have two short questions. One is, have you considered for each of the models that you have there, what would be the contribution in X-rays, either from synchrotron or from synchrotron self-Compton, even just to make sure that you're not overproducing the very weak X-rays that are there?
Yes, so we do have a cooling break, and if you extrapolate the cooling break all the way to the X-rays are a little bit above. So there has to be some additional X-ray components.
Right, but my concern is that synchrotron self-Compton might overproduce in some models the emission compared to what you see. So synchrotron itself maybe is below the flux that you see, but synchrotron self-Compton could give you a significant booster. And the other question was about polarization? Is there any way that we can get polarization in the radio?
I'm not super familiar with, I don't have a lot of experience with polarization in the radio. I don't know if it is necessarily bright enough to do that. But I certainly think it would be interesting, especially for rolling out the jetted case.
Yeah. Okay. Thank you.
Okay, any other questions?
Maybe just a comment, but just thinking about these jets, I think it's important to distinguish GRBs or things where we have a very short, a short central engine that is basically impulsively injecting energy into the medium versus, you could imagine it's, okay, some point we have a state transition and now we turn on a jet and let's say it has more or less constant luminosity and it's sort of more of it's like sort of inflating a bubble. I guess you can model it as a shock with energy injection, I guess. I think it would be interesting just to develop those models more because I mean that would be a natural way to add energy as well. It's just to have a steady jet rather than the impulsive scenario we usually study GRBs.
Yeah, can you go back to your Lorentz factor constraints in various cases? Yeah, here. Yeah, it's a bit strange. Maybe Tasvir can comment on this as well. So let's look at the yellow case. The observing angle is 90 degrees, okay? And the Lorentz factor is 10. And the jet is beamed with the 10 degree, let's say, wide. Why are we still seeing the very bright radio emission? Because I'm looking at the yellow, gamma beta is 10, so everything should be beamed 90 degrees away from our line of sight, right? So there seems to be something that's a little strange in this case.
Yeah, but in this case, the jet is expanding at constant velocity, but it's sweeping up more and more material. So this is the reason you have a lot of more and more electrons emitting, so it can produce brightening. Yeah, but even taking into account the beaming effect, still, yeah, but there's also problem, a kind of problem. In this case, the radio light curve is already declining, starting declining. So this is completely opposite what's happening in HYZ. So HYZ case, the light curve is steeply increasing. So then maybe, yeah, so I'm not sure. So.
Okay, any last questions?
So for a external medium that is very steep, I guess the contribution mostly comes from the electrons swept at the beginning, or I'm not really familiar with the model.
Yeah, so if you, which is another issue with, this off-axis case, is if this is a really steep density profile, which means that if a jet has not decelerated at this time, you would have to sweep up a lot of mass, which, increases your energy budget needing a jet to be, have a lot of kinetic energy and have a lot of mass ejected in it. Yeah, it is puzzling to me. I think what is interesting is that it's comparable to the off-axis jet model to HYZ, which showed a similar really massive, large swept-up mass calculation. Because if you extrapolate this, obviously there has to be some core density. This doesn't go off forever, but it is sort of somewhat similar to what you would see for 2018 HYZ, given the same model.
Thank you.
If you do have a density profile that declines faster than r to the -3, you actually change completely the evolution from what you have with the shallower density profiles, and you can start accelerating the jet rather than decelerating. So the whole dynamics change qualitatively in that regime.
Nobody wanted to stand up, but the speaker is evident.
No, yeah, so yeah, since we're making comments on the density profile, I know you already know this, but the r to the -2 is also what you expect for a freely expanding jet. So that is still a good model here. And this source is also possibly in AGN in the past with radio emission. So you actually have a good
reason to have this internal emission because there is nothing to run into, so it's not an external medium, but it's the material that is actually in the outflow that we're measuring here. So this is, I think, a third model that's sort of following up on Brian's comment.
Okay, let's thank Collin again.